Hello everybody, Mr. Brown here, and in this presentation we are going to discuss mass spectrometry. This is yet another technique that we use in the organic chemistry laboratory to elucidate the structure and other information about our molecules. So if you'll follow along with me, I'll tell you about the theory behind this technique and the information that we can gain from it. So I will start off the discussion of this by pointing out the difference in the word spectrometry here from the word spectroscopy, which is the word that we've used in a lot of the other techniques that you've learned about in your introductory and organic chemistry course thus far, where spectroscopy indicates a technique where we are studying the interaction between matter and light. Spectrometry is a little bit different. In mass spectrometers, we're investigating the interaction between matter and something other than electromagnetic radiation, and in this case, it's an electron. And then, oddly enough, we still use electromagnetic radiation to investigate the interaction. But besides that, in any case, the overall idea behind this technique is used to determine the molecular weight and molecular formulas of our compounds, and it's also heavily used as an identification tool for unknown compounds today in different environmental and forensics labs, and I'll show you an example of that here shortly. But I've got some images of some mass spectrometers here behind me. You can see very often you find them in labs connected with liquid chromatography instruments, and that's what this instrument here is. But right behind me here, this would be the mass spectrometer, and I have kind of a blown up view of it on the next page, and we'll talk about how it works. But what they're going to do is we introduce a compound that we want to study in them, and then we vaporize or we bombard that compound with high energy electrons, and that causes them to fragment in certain patterns, and we study the fragments that this causes. So as I said, taking a look, we'll move to that next slide, and we'll see kind of in cross section of that tube that was just sitting there behind me has of course a high tech array of different pumps and detectors and energy sources that generate high energy electrons, and it's somewhat like an electron gun in this enclosed tube. And we introduce our target molecule into the tube and we shoot it with these high energy electrons. And what happens is sometimes one of these high energy electrons that we are firing at our molecule is struck by one of these electrons, and it knocks an electron off of our target molecule, and it causes one of the electrons in one of the bonds on our target molecule to be ejected, to leave that molecule. And what it leaves behind is now what we call a molecular ion, and it's kind of an odd species. It's a little bit of a mix between a radical species and an ionic species. So it's a molecule that is missing one electron in one of its bonds. Since it's lost one electron, overall it has one positive charge. It has a positive charge, and one of the bonds is considered a radical bond now because it's only one electron, where normally a bond is a pair of electrons. And sometimes this molecular ion, as it were, makes it to the detector unscathed except for the loss of the one electron. Very often this molecular ion fragments or breaks apart into two different pieces, and one of those pieces has the charge in that it has a carbon atom missing two electrons and therefore has a positive cationic charge or is a cation. And then in the other species, we have a radical species, and that radical species, while it's neutral, it's still a radical because it's a carbon with three bonds and just one electron that's not bonded into anything. But and that's not a very stable state for carbon. That's considered a radical, and so we'll take a look at that. So after all of these fragments or break up or are formed from shooting these electrons at our molecules, they then are subjected to a magnetic field. So we have these charged particles that result from our molecules having electrons fired at them and then subsequently having electrons ejected out of the bonds. We have all these charged particles, and some of them are the parent, the molecular ion with the missing one electron, and some are the fragments that results after that falls apart. And they are subjected to this magnetic field, and after the magnetic field there is a detector, and the magnetic field will affect these charged particles with different force depending on their mass. So smaller charged particles are deflected more greatly than larger, more massive charged particles, and therefore we can use our detector to determine what different masses of fragments are there. And so we can set up and get a spectrum of the masses of these fragments that result from the mass spectrometry. And so then we can know that the biggest fragment there is the overall mass of our target molecule. And that's one way, that's one piece of information that we can get from the mass spectrum, is the mass of the molecular ion peak, which will be essentially the mass of the parent molecule. So we can put an unknown molecule in, and it should spit out on the other end its molecular ion peak, or the molecular mass of that molecule. So I like to start with a little bit of an example that may seem on the surface a little far-fetched, but really, if you look at where this science is going today, isn't so far-fetched. And I have an example here. What you are looking at is the mass spectrum. It's the output of mass spectrometry conducted on some unknown powder. And I always like to think about this in terms of your favorite forensic criminal investigation show, because they always treat the mass spectrometer as the miracle machine. If you're paying attention, it's the instrument they use when they take the unknown substance and they throw it in some big box, and it spits out the identity of the substance on the other side. And it's always the mass spectrometer that does that. And this is the graph that a mass spectrometer actually generates. And while mass spectrometers can't tell you what is on the other side, it can do, like I said, if you kind of look at the output here, what you're looking at on the bottom is the mass to charge ratio. And we just assume that since most of these ions have a charge of 1, that these are just typically molecular masses down here on the bottom. So we can see that most of these are fragments of the parent molecule that have fallen apart, but there's one small peak down here at the very end that would be the molecule with just one electron removed, and we see that small peak at 149. So I know the molecular weight of this molecule is 149. Furthermore, if we also know that because of the way these fragments or these molecules tend to fragment in patterns, the whole spectrum itself, the different fragments that are produced are, again, like we saw with the IR, they're something of a fingerprint. Molecules make unique, reproducible fragmentation patterns in mass spectrometers. So I can compare these against libraries of known spectra of molecules and see if I can use that as an identification tool. So given a library, it can compare against other molecules of known spectra of other molecules and tell you what this unknown molecule is. For example, as you might see on your favorite forensic show, we put this unknown molecule in that seemed to kill somebody, and we compare it against our suspected culprits of acetaminophen. So regular aspirin, regular Tylenol, and that doesn't seem like that good of a match. Or methamphetamine could be what we found at the scene as well. That seems really pretty close. And notice we also see the 149 matching molecular ion peak down there. And then finally, we were kind of concerned it could have been very deadly VX nerve gas. And there is a large base peak on here like we see on our graph, but we see that the molecular weight of VX compound is 251, so that's a pretty good indication that that's probably not a good match there. If we line it, we really saw pretty close similarities to that methamphetamine spectrum, and if we line the two up beside each other, we do see that it would match, and we could say, hey, oh, look, looks like our unknown compound, the result of the death was an overdose on methamphetamine. And indeed, if you go and look, and we would see that the molecular weight of that molecule is 149. So we could use that as evidence for, hey, this is our unknown molecule. Not only can we use that as an identification tool, we can put a completely unknown compound, we can put in the mass spectrometer and determine the molecular weight. And we'll discuss in a few future slides how we can use that to start to deduce what the overall molecular formula might be. So while you can't put a completely unknown molecule in the instrument and have it just spit out, hey, this is the identity of that, it is a piece, it does generate data that, along with other application of our techniques, the IR and the NMR, do lead to the discovery of the identity and structure of the completely unknown molecules. And we'll talk about in the rest of this presentation the other things we can learn about the fragments from these mass spectra. So by this point you may have noticed, or probably have noticed, that the molecular ion peak, the one with the highest mass, is usually not the tallest of the peak, and I'll explain where the height of the peak comes from. So the highest peak is what we call the base peak. It's kind of confusing. We want to be clear that the base peak is the highest peak in the spectrum. The base peak is not the molecular ion peak. It does not represent the molecular mass of the compound being studied. The base peak is just the tallest peak. It's called the base peak because it's assigned an abundance of 100%. We just say that's the one that is being seen the most, so that signal is 100%, and then every other peak is given a percentage compared to that. If that one's 100%, everything else is X% compared to that, and that's just how the signal comes through. That doesn't really it really doesn't give us much data other than which fragments might be most abundant in their masses, and we'll talk about how that can be used a little bit later in the discussion. But one of the big things we can get from this information is, for smaller molecules, we can use this to determine how many carbons are present in this particular molecule, and I'll give you some examples on that coming up. The molecular ion peak, the last note on this slide here, the molecular ion peak is always the most intense peak in the cluster with the highest mass to charge ratio. So what that's saying is The molecular ion peak is the one. So if you look furthest down the mass part of the spectra that a mass spectra returns, then the molecular ion peak is going to be the one. You find the last group on the end here, and the molecular ion peak is going to be the most intense peak, or the peak with the highest abundance, the highest percentage in that group. Now, it's maybe important to hear. It may be important to note here that sometimes, not all mass spectra, especially when the molecules that you're studying get larger, not all of them will have a molecular ion peak at all. Sometimes the molecular ion peak is so relatively non-abundant that it doesn't show up on the spectra at all, that you only see some of the fragments. When you're studying really large molecules, that's still useful, and there are ways that it still can be applied. But for our purposes, while we're learning this in my class, you can assume that the molecular ion peak, unless told specifically or explicitly otherwise, the molecular ion peak is going to be the tallest peak down in the last cluster with the highest mass to charge ratio. And so you can infer the tallest peak down there at the end as, again, the molecular mass of the compound that's being studied. And we'll talk about how this base peak percentage assignment will lead to us being able to determine how many carbons are in that molecule coming up. So, a little bit more about the information that you have when you were able to identify the molecular ion peak, and what you know once you know the molecular weight of an organic molecule. Something you may not realize you now know is you now know whether or not there are nitrogen atoms present in even or odd amounts. And let me explain. We know, and this is kind of a guiding principle for simpler organic molecules, one that you'll encounter in an organic chemistry class. Our simple organic compounds only have carbon atoms and hydrogen atoms and oxygen atoms and nitrogen atoms, and then sometimes some halogens too, which we'll speak of in a minute. But just for the moment, consider molecules that only have the carbon, hydrogen, oxygen, and then sometimes some nitrogens. So carbon and hydrogen must come together in even amounts. So even though the hydrogen and the carbon are or even though the hydrogen is odd, it comes in even amounts with the carbon atoms. And so um, if you have molecules that have even molecular weights, then those molecules probably don't have, or can't have, a nitrogen atom unless they have 2 or 4 or 6 nitrogen atoms. And for most of our simple molecules, that is in effect saying, hey, this doesn't have a nitrogen atom. Whereas if it's an odd number, or if it's an odd molecular weight, the only way we get there in kind of a simple molecule is by the presence of a nitrogen atom. And so, especially for the molecules and the identification that you'll run into in the introductory organic chemistry class, having an even molecular weight means that the nitrogen atom is not there, and having the odd molecular weight means that this molecule has a nitrogen atom somewhere in its structure. Now, like I said, you might ask at that point, well, what about if we have a chlorine or a bromine? Now, the answer to that is, well, chlorine is actually, even though it's in the next column of the periodic table beyond oxygen, where you would assume that it has an odd atomic weight, it actually has an even atomic weight. Go check the periodic table. Bromine has one that's in the middle. It's 34. I looked it up a minute ago, but it would be, go, and there we go. Bromine is, oh, sorry, I have that backwards. So bromine is rounded to an even number, 80. and chlorine is in the middle, 35.45. So I mean that's really close to either 35 or 36. So depending on how you um, consider chlorine, it can be odd or even. It could be odd. So you might say, well, what if it's got a chlorine atom? And well, the answer to that is in just a moment we'll talk about how chlorine and bromine have distinctive patterns where we can identify when and if a chlorine atom or a bromine atom are present from a mass spectrum. So, continuing on, a little bit more about this molecular ion peak and something known as the molecular ion plus one peak. And if you were looking really close on the past few slides when we talked about the uh, relative abundance and the base peak, and I said that the molecular ion peak can always be found. We'll go back. The molecular ion peak can always be found at the most intense peak in the cluster with the highest mass to charge ratio. So in this example down here, for instance, we've actually got the peaks laid out for us and labeled for us with their relative abundance clearly labeled and their mass clearly labeled on each of those peaks. And we see the molecular ion peak for this unknown molecule has a mass of 86, and it tells us that that is the molecular ion peak. That's what the M plus dot symbols is, just the parent molecule that's lost one electron, so it's got a positive charge. It is a radical species, but everything is there, nothing, it hasn't fragmented yet, and overall that has a mass of 86. But there's another peak there, a peak of 87. So where does this one size bigger peak come from? This one atom, it seems like it's one hydrogen atom bigger. But you got to think this instrument doesn't add an atom to a molecule. So how do we get one bigger? How does a molecule grow by one size? And what that comes from is keep in mind, think all the way back to general chemistry where we talked about isotopes of our different atoms. Out there in the universe, about 1.1% of the carbon atoms that exist are not carbon 12, they're carbon 13. They have one extra neutron in their nucleus. And so that extra peak that we see there, that's why the molecular ion peak is always the tallest one there, because the molecular ion is going to be most of them are going to be all carbon 12, but a 1.1 percentage of them are going to include one carbon 13 in their structure. And so normalizing them to 100% allows us to exploit this factor, in fact, to be able to determine how many carbons are in our molecule using this information. Now, it's important to say that this really only works for smaller molecules. The rounding errors get too great for this to be of use, particularly for molecules any larger than about 8 carbons, but it's useful for evaluation of molecules of the size that we see at this level. So we teach it and we talk about it some, and I'll show you how to calculate a few examples on the next few slides. So now we're going to put those ideas into practice. We're going to take this mass spectrum that we have here of this simple unknown compound, figure out how many carbons are in that compound, and then we're going to use some critical thinking and figure out the overall molecular formula of that compound given that information. So we see that we have a molecule that has a molecular ion with a weight of 86 atomic mass units, because we're given this mass spectra and somebody has nicely labeled each peak and given the numerical abundance for each. So hopefully we could identify the molecular ion as the ion with the tallest peak in the grouping with the largest mass. So the grouping with the largest mass is the one all the way furthest down on that side of the table, and we see a couple of peaks near 85, 86, and 87. So the most abundant peak in that group is going to be your molecular ion peak. That is your regular molecule that's had one electron removed, so it's just the molecule with a positive charge and a mass, and that mass is 86. So every atom added up off the periodic table for the molecule should equal 86. And we see that the molecular ion plus 1 peak is therefore must be 87, and we're given the relative abundance there of 1.2. So the molecular ion peak itself has an abundance of 20.9, and the M plus 1 peak has a relative abundance of 1.2. So we can compare those two abundances to figure out how many total carbon atoms are in our molecule. The way we do that is we take the 1.2 and divide it by the 20.9 and multiply by 100%. So 1.2 divided by 20.9 times 100 equals 5.74%. So about 5.74% of our molecules have had one of the carbons replaced with a carbon 13 instead of a carbon 12. 95% of them have all carbon 12s. 5% of them have some carbon 12 and one carbon 13. If we take that and divide it by the fact that on average there are 1% or 1.1% of carbon 13s out there in the universe, we divide that by the 1.1. So you divide that by 1.1, it comes up to 5.2, and we're going to say that that means that there are 5 carbons, so that rounds pretty neatly to assuming that there are 5 carbons total in our molecules. So since about 5% of them have one of the molecules replaced, and each one of those molecules would contribute to 1.1% to that probability, that means that we probably have about 5 carbons in our molecule. And for something that small, we can make the assumption that there are 5 carbons in that molecule. So now we know the atomic mass or molecular mass of the molecule, even though we don't know what the molecule is, and we know how many carbons are in there as well, because we have the molecular ion peak and the molecular ion plus 1 peak. So, and what we know is 5 carbons contributes 60 AMUs. So we know the formula must start with C5. So we're assuming there's 5 carbons, we know that. If we had 5 carbons and they were all filled out with hydrogens, if we take the case of a completely saturated hydrocarbon, then we would know the weight of this molecule would be 60 wrapped up in the carbons, and then we would have 12 hydrogens for a total weight of 72. So the formula can't be just plain C5H12, because that would only give us a mass of 72. So we have to have something bigger in there. And we know that it's not going to be a nitrogen atom, because this particular molecule has an even mass. And when we have an even mass, that generally means we don't have, we have 0 nitrogen molecules, or we have 2 or 4. And we're just pretty much assuming we don't have a species with 2 or 4 nitrogens or anything like that. So there's no nitrogen atoms. So that means there must be an oxygen atom in there probably. So if there's one oxygen atom in there, then C5O, and so now an oxygen atom would add 16 to the mass. So that means If I have 60 total mass in the 5 carbons and then 16 from the oxygen, I'm at a total of 76, which means I can have 10 hydrogens in that case. So it's likely that the molecular formula of this molecule, just from the information that we have 5 carbons and a molecular weight of 86, I can infer that the molecular formula of this molecule is likely to be C5OH10, and it was probably be written C5H10O instead. That's generally how we have it written. And an astute chemistry student can take that that molecular formula and start to draw. You could probably quickly draw all of the relevant Lewis structures for different isomers that are possibilities of that molecular formula. So in another example here, we are going to again try to figure out what the chemical formula of a compound given just this mass spectrum. And this time we're even going to try to propose a structure. So we start by looking at the mass of the molecular ion, and we're given again the relevant information in kind of a direct way. We're told that the molecular ion has a mass of 54, and it just happens to be the base peak in this particular spectrum. And the M plus 1, the molecular ion plus 1 peak, which results from a molecular ion having one of its carbons replaced with a carbon 13, has a mass of 55, and it has a relative height of 4.6%. So in simple molecules, to figure out how many carbons are present, we can compare those two numbers. We can figure out how much, by comparison, our molecular ions have a carbon 13 replaced. And most of the time you do your 4.6 or your molecular ion plus 1 peak divided by the abundance of the molecular ion peak times 100. In this case, since the molecular ion peak is the base peak and does have an abundance of 100%, doing 4.6 divided by 100 times 100 will just result in 4.6. So we know in this case the molecular ion plus 1 peak is or has 4.6 relative to the molecular ion peak. So we can skip directly to the calculation where we divide by the fact that all carbons have a 1.1% chance of being a carbon 13. So if we take 4.6, if we do just that, if we take 4.6 divide by 1.1, we get approximately 4 in this case. So again, we're going to assume that the approximation works for simple molecules, simple small molecules. So this is going to be a 4-carbon molecule, and this 4-carbon molecule has a mass of 54 total. So 4 carbons has a mass of 48 total. So if we're assuming a 4-carbon molecule with a mass of 54, there's only one option there, and it's an organic molecule and doesn't include anything kind of exotic. There's only one option, and that is going to be C4H. So C4 is 48. To get to 54, you just need 6 more hydrogens, C4H6. And again, with such a simple formula by this point in the organic chemistry course, I would hope that you guys could draw structures that may, or draw good Lewis structures that satisfy octet rules and satisfy this chemical formula. And if you want to pause there and wait a moment, I will show you all of the possible structures for that formula on the next slide. And it will be coming up in just 3, 2, 1, now. So those are all the possible structures of C4H6. If you drew any one of those structures, you would be correct and have a correct Lewis structure that um, accounts for that chemical formula. So now we're going to take a look at what we interpret when we look down at the large, massive group down at the very end of the spectra and see not only an M+1 peak, but also an M+2 ion peak. And this is the pattern that we see. I've alluded to a few times that there's a special pattern that you see when you have halogens in your molecules. And this is a way that you can look at a mass spectrum of a molecule and know that there's a halogen present. So as we're talking about, when you look at a mass spectra and you look down at the peaks at the furthest end of the spectrum, which have the most mass, this grouping down here, as we've indicated earlier, is going to contain your molecular ion peak. It's going to have the peak of just the molecule with the one electron knocked free, and so it has a charge, but it also has the same mass as the parent molecule, if you will. Sometimes we see that there's kind of two large peaks in this grouping down here, and the first one is always going to be bigger than the second one, but we have our molecular ion peak first, and then a molecular ion peak following it, and then a molecular ion +2 peak after that. And we get these types of patterns when we have the bromine and the chlorine, because chlorine and bromine have two major isotopes. So carbon, nitrogen, and oxygen have a really dominant isotope. Carbon 12 is 99% of the carbons out there. And but unlike chlorine, chlorine has chlorine 35 and chlorine 37, and it's about 65-35. Bromine has bromine 78 and bromine 80, and they're almost 50-50. So their ions, the either one of those is likely to be found in a molecule, and so it arises in molecular ion peaks that are much more close to the same size as each other. And so anytime we see a molecular ion peak that is followed by a molecular ion +2 peak, and if the molecular ion peak is 1/3 of the size of or if the molecular ion +2 peak is 1/3 of the size of the molecular ion peak, then we know that the halogen is chlorine, and that kind of looks like this right here every time. So the molecular ion +2 peak, this is the representative of the molecular ion peak with the heavier chlorine, and this is representative of the molecular ion peak with the lighter chlorine. And the lighter chlorine is about 65% abundant in the universe, and the heavier chlorine is about 35% abundant in the universe. So the height of this peak is always going to be about 65% relative, 35% relative to this one. So about 2/3 to 1/3 for these two peaks. If there's a molecular ion peak and a molecular ion peak that's much closer to 50-50, then that's always a bromine. We can see the bromine here. We know there's a bromine in that molecule because the two isotopes of bromine are much closer to 50-50, so it's really likely, or it's about equally as likely, that either isotope of bromine is found in, for instance, in this molecule here. If I have a bottle of bromocyclobenzene or bromobenzene on my shelf, about 50% of them are going to be light bromine, and about 50% of them are going to be heavy bromine, unless I've specifically selected for one or one of the either isotopes of bromine, which gets really expensive. So it's probably not that. It's probably just regular bromobenzene with about this 50-50 mix of heavy and light bromine. And so this is the patterns that we see. We look out for these patterns. We can use these patterns to determine if there's a halogen present or not by just looking at a mass spectrum of a molecule. So here's a mass spectrum of an unknown compound, and we might be asked to determine if there is a halogen present or not. And we can look down at the heaviest group of ions generated in this mass spectrum in this group here. And we do see two kind of large peaks in this part of the spectrum. So, unless told otherwise, we are assuming that the largest peak in the last grouping of peaks is the molecular ion. So, it looks like this molecular ion has a mass of 76. There is a molecular ion plus one peak of 77 mass, and it has a 1.7% abundance. And then there is a molecular ion plus two peak of 78 mass at 8% abundance. And so we would say, okay, yeah, it does appear that there is a molecular ion as well as a molecular ion plus two peak in this sample. That means there is probably a halogen present on this molecule. Furthermore, we can see, even especially from the numbers here, that the molecular ion plus 2 peak is about 1/3 the size of the molecular ion plus 1 peak, the molecular ion peak itself, with a relative abundance of 25. So 8 times 3 is 24. It's really close to exactly 1/3 of the molecular ion peak. So I feel really comfortable in assuming that there is a chlorine on this molecule. Now, I do want to point out that once you involve a halogen, it screws up the percentages of what atoms are present in the molecule. So the estimation of how many carbons are there doesn't work as well as it or doesn't really work like it does when a halogen is not present, because if we try our trick here where we determine how many carbons are in this molecule, then we would divide the molecular ion plus 1, which is 1.7, by the molecular ion, which is 25.3, and 1.7 divided by, and we multiply by 100 as well. Can't forget that part. Trying my best to forget that part. Multiply by 100. 1.7 divided by 25.3 times 100 is about 6.7%. So about 6.7% of our molecules have a mass of 77. And if we divide that by 1.1, it tells us that approximately 6 carbons would be in our molecule. And if we think about that pretty quickly, 6 carbons means that we have a base mass of 72, because each carbon has a mass of 12. But if we have a base mass of 72 with 6 carbons and a total mass of 76, then we only have room for four more hydrogens, which is really impossible to begin with. We definitely don't have any mass left over to put a chlorine on there. So that's just to say that part of that 1.7% of the abundance of the molecular ion peak just comes from having a chlorine that's one bigger, not from having a carbon one that's one bigger. So those percentages get messed up. So you can't really rely on that technique anymore once the halogen pattern arises. My best guess would be to say there's 3 carbons on this molecule, which puts us at a base mass, if you will, of 36, and then you can add 35 halogen in there for a total of 71, and then you have room for 5 hydrogens, and that probably means you have a double bond somewhere in your molecule, but that's just a guess. So based on the fact that we have a total mass of 76, you can't say for certain. However, we do know that there's not 6 carbons, and that our trick for finding how many carbons there are is kind of out the window when there's halogens present, but we can determine that there's a halogen present, and we can determine that it's chlorine. Now that we've talked about the molecular ion and really pointed out everything we can learn from that and the group that it's located in, let's talk about the other peaks you're probably wondering about by now that appear further to the left side of the spectrum. Why do we see those other peaks and multiples of them, and why are many of them bigger than the molecular ion peak? We're going to answer all of those questions in the next couple of slides. So we can gain some information there with some analysis we can do on the so-called fragment peaks that we see down further closer to the front of the spectrum. And we see predictable patterns of these peaks across the mass spectra of different molecules. And these fragments come from the fact that once these bonds have been compromised by having an electron knocked out of them, many times the molecule goes ahead and falls apart. And when it falls apart, it falls apart into two pieces, and one piece keeps the electron and becomes a radical. Now, once it falls apart, it's no longer charged. That carbon, these carbons here that you can see, they keep the electron. They're a radical species because they don't have a charge because they have the electron, but they are radical because they don't have a bond on that electron, and electrons like to be paired and bonded. So it's still a reactive situation even if it's not carrying a charge. Now, the other side has the carbocation. It has a completely charged carbon now because that carbon's missing electrons and bonds. It's just a 3-bond carbon with an empty p orbital. It is a everyday carbocation. Predictably, when the piece that falls off is a methyl group, a methyl radical, a CH3 with a electron making up for one of those bonds, the ion that's left over is whatever the molecular ion, that's what M represents, molecular ion, minus 15. So to lose a methyl group, you always lose a mass of 15. So we predictably see peaks at the molecular ion minus a 15 charge. And we know that comes from a methyl radical being kicked off of the parent ion. We know that the peak that appears at M29 appears because an ethyl radical has been knocked off of our parent molecule. So in the example we have here, if the parent molecule has 5 carbons, or is kind of a regular pentane, then the molecular ion, the mass of this thing is 72. Then we would expect if one of these gets removed and leaves an ion that has just this end of the molecule, then we would expect a big peak at 72 minus 15, which would be 57, and this is where we see the M minus 15 right here at 57. So we can predict what ions may form, and as you may have guessed by now, forming stable carbocations is preferable. So when we can form stable carbocations, that leads to big peaks. All right, and those are our most abundant peaks. So we'll look at a couple of those examples on the upcoming slides, and we'll do those next. So here we have a look at what I was saying on that previous slide. If we look at the mass spectrum for 2,2-dimethylpentane, which has this structure here, if we consider this to be the molecular ion, so we're assuming that one of these bonds has had its electron removed, so one of them is a radical bond currently, and this thing has a positive charge. It still has the same mass as a regular 2,2-dimethylpentane, so it has a mass of 100. Well, we look at the mass spectrum and we notice that there is a big peak. The base peak is actually at 57. So we might be interested in trying to determine what does that mass 57 fragment look like? And an astute reader of mass spectra would notice that if the parent molecule has a mass of 100, and we do see the parent molecule down here, the parent molecule really likes to fragment because the molecular ion peak is very small. So that means not many of the molecular ions intact made it to the detector. Most of them fragmented into different pieces. And the majority of them fragmented into a fragment that had a mass of 57. And like I was saying, an astute reader of a mass spectra would notice that if the molecular ion has a mass of 100, the base peak has a mass of 57, that means our molecular ion is very often losing a chunk that has a mass of 43. So what fragment has a common mass of 43? That would be a propyl fragment. A 3-carbon fragment has a mass of 12, 24, 36, 38, 40, 43. So once you kind of figure that out, you say, oh, well, that means our 2,2-dimethyl has lost a propyl group to result in an ion. And if we look at the structure, we can see that if we lose the propyl group at this juncture or at this bond, the resulting carbocation is tertiary, and forming stable carbocations is preferable in any kind of situation. So we're assuming that the fragment with the mass of 57 will have this structure here, and the lost uncharged radical that's not detected that has the mass of 43 is the propyl radical as we view there. And we can make other predictions about what the masses of these other fragments might look like, but that's the most abundant one because that's that one leads to a tertiary carbocation. Now we can make the tertiary carbocation by losing this bond here. Notice if we can sever that bond there and make a tertiary carbocation here and a methyl radical. And the methyl radical, remember from the previous slide, the methyl radical has a mass of 15. So we would expect a kind of large peak at m minus 15. And we do see a decently large peak at m minus 15. But why don't we see as big of a peak at m minus 15 as we do at m minus 57? And that's because radicals have stability very analogous to carbocations, in that tertiary radicals are more stable than secondary radicals, which are more stable than primary radicals, which are more stable than methyl radicals. And so in this case, we have a methyl radical. In this case, we do have a primary radical, which is not very stable, but it's more stable than just a plain old methyl radical. So it's more likely for these two species to form than it is for these two species to form. So that's why we see a more abundant peak at m minus 43 than we do at m minus 15, even though we do see some of the m minus 15 peaks. Okay, we have an example on this slide that says, although 2,2-dimethyl hexane has a molecular weight of 114, no peak is observed at 114. So the base peak in the mass spectrum occurs at m minus 57. Draw the fragmentation responsible for formation of the m minus 57 ion and draw the ion. Explain why this cation is the most abundant ion to pass through the spectrometer. Can you offer an explanation as to why the m minus 15 peak is not the base peak? So we'll look at the spectrum of 2,2-dimethyl hexane, and we'll consider the structure of 2,2-dimethylhexane. So there's hexane, 2,4,6, and 2,2-dimethyl would put some methyl groups on the number 2 carbon, and that would be the structure for 2,2-dimethylhexane. And it says the base peak occurs at M minus 57. So as we saw in the previous slide, I'm going to first assume that the molecular ion that is formed, so M minus 57, it says the molecular weight is 114. So M minus 57 turns out is 57. And so I'm going to assume that the carbocation that is formed looks something like that, with 4 carbons and 9 hydrogens. That would have a weight of 57 itself. Now, to get from this structure to that structure, I have to sever this bond there. Now I'll go and check. Now that looks like 4 carbons are being chopped off, so it would be CH2, 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 CH3 that are being removed. So again, that is 4 carbons and 9 hydrogens, so that is a mass of 57. So it makes sense for the M minus 57 peak to have lost this butyl structure here, this butyl radical here. This is what we've lost, is a butyl radical. And for the molecular and for the ion responsible to have a weight of 57, it would look like this tertiary carbocation here. And it makes sense for that to be the base peak because it is a tertiary carbocation. And the next question basically asks, why do we get this fragmentation rather than a fragmentation of just one of the methyl groups? I.e., why don't we just split one of those groups to make a larger tertiary carbocation? And the reasoning is the same as before, where that results in a methyl radical that is not as stable as the butyl radical. So we can make a decently stable butyl radical by severing that bond, and a really stable tertiary carbocation by severing that bond, which is why the M minus 57 peak is the base peak in this particular mass spectra for 2,2-dimethylhexane. We have another example here of a mass spectra analysis question that says the following are mass spectra for the constitutional isomers ethyl cyclohexane and 1,1-dimethylcyclohexane. Based on likely fragmentation patterns, match each compound with its spectrum. So they want us to figure out which of these is the spectrum for ethyl cyclohexane and which is the spectrum for 1,1-dimethylcyclohexane using likely fragmentation patterns. So let's consider the structure of these two compounds. Ethyl cyclohexane, let's draw a cyclohexane and let's put an ethyl group on it. 1,1-dimethylcyclohexane, draw a cyclohexane, put some methyl groups on carbon number 1. So just quickly surveying these structures, I would say the most likely fragmentation pattern for ethyl cyclohexane would sever that bond, which would result in an ethyl radical and a secondary carbocation, CH2, CH3 with the... So ethyl radicals have a mass of 29. So we would expect the mass of the resulting secondary carbocation We couldn't form a tertiary carbocation by severing any of those bonds, so the resulting secondary carbocation should have a mass of M minus 29. The molecular ion has a mass of 112. We can see that in both cases. It makes sense if we add up all of the mass of the parent ion or the parent molecule, we would see that it would be 112. And so we expect a base peak, or we expect a really prominent peak at M minus 29 for ethyl cyclohexane. 112 minus 29 is 83, and this spectra has a big base peak at 83. So I'm assuming that this is the spectra for ethyl cyclohexane. But just to be certain, let's see the other spectra over here and see if we can make sense of why we see some of the particular fragmentation patterns for that molecule. And if we consider 1,1-dimethyl cyclohexane, I'll draw it a little bit bigger right here. It really makes sense to have a really prominent peak that breaks one of these bonds there, one of these methyl groups. By losing one of those methyl groups, we form a tertiary carbocation. And of course, we do have our methyl radical that we removed to do that. So we would expect a big base peak at M minus 15. To get that tertiary carbocation, we remove one methyl radical. A peak of M minus 15 would show at 112 minus 15, which would be 97. And we do see a base peak of 97 in this molecule here. So it makes sense for this to have given us a big prominent peak and base peak at 97 for that molecule, and that is what we see in this case here. So we're assuming that this is the 1,1-dimethyl cyclohexane mass spectra. So as you are using IR spectra along with your now learned skills for mass spectra analysis, something that is useful for starting to determine the structure of a molecule is calculating the degrees of saturation or the hydrogen deficiency index of a molecule. Once you know the chemical formula of an organic compound, you can calculate the degrees of unsaturation by using the formula that you see here on the slide. The hydrogen deficiency index is equal to 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus total halogens in a molecule. So doing this simple arithmetic calculation will lead to some integer. And that integer represents the degrees of unsaturation of a molecule, where a fully saturated organic molecule only has sp3 carbons bonded to hydrogens. A degree of unsaturation represents either an enclosed ring in the molecule or one pi bond in the molecule. So 2 degrees of unsaturation can represent 2 double bonds or 1 triple bond, or 2 rings, or even 1 ring and 1 double bond. 3 degrees of unsaturation, for example, could be 3 double bonds, or 1 triple bond and 1 double bond. So that degrees of unsaturation will at least start to give you some idea as to possible structural components of that molecule just using the chemical formula, which you can sometimes get from just doing a mass spectra and maybe including some IR spectra information along with that. Of course, later on in the course, we're going to learn how to use NMR spectroscopy to really wrap it all up together and determine overall structures of our molecules. But up until that point, we can at least start to predict what structures may be available to us in that molecule.